So yeah, this is the second slide we have. It's more basically if you guys are new for the second class, this is our second lecture on complex numbers. And so there is a domestic uprise on attendance. So if this is your first lecture, you might want to stick around. That's what like it was about attendance. And now if we go to what we did in the last lecture, right? So it's more about let's have a question so we can get any doubts clear if you guys were present. So can you tell me what would be this representation of the following number? If you guys were not in the lecture, it's also fine. We will discuss it briefly towards the answer.
I'd like to ask though, Shahid, what are complex numbers? Let's start off with that for the recap. What are complex numbers?
So if we are starting with the recap, it would be complex numbers are basically numbers that have a particular representation or a particular component of them that contains a square root of a negative number. So for our simplicity, we have named it to be square root of minus 1. So if there is any number that has the presence of square root of minus 1 in it, it is a complex number. So that is what is represented by iota or I in the number. And there are different ways to represent the number. There are like the polynomial or algebraic form in which the number is given. There are also the Euler form and the polar form that are two different forms that are useful if when we are dealing with different kind of problems in which complex numbers arise. Now, if we move towards the representation, so this is if you guys missed it, these are the representation. So on the right side, we can see that z equals to x plus iota. It is given in this form, the number. And the other two forms are in terms of r and theta. So this is the polar form and this is the Euler form. And this is the answer based on the trigonometric identity knowledge of what the value of cos and sin theta are for pi by 6. Yeah. This is how it is solved. So for the solution, it would be basically if we see root 3 and 1, so we divide the number by its modulus so that it is in the form where r is equal to its modulus. We'll talk about it later in brief, but and this is about what we did with algebra of the complex numbers. So it's about division, multiplication, what we do with that. So this question we can see that if we see the solution, it is this is the question here. So we multiply and divide by the conjugate of the number, which we talked about. The conjugate of a complex number is the number in which the imaginary part is of the opposite sign. So for minus iota, the conjugate is 4 plus iota. We divide and multiply it with the number, and in the denominator, it just becomes a real number, and we solve the numerator by basically multiplying, in which iota square is replaced with minus 1, basically 11 minus 12 minus 1 11. So this is what we did in the last class. Now if we can jump on the Jamboard for a second. So the next topic that we are going to cover is about how what complex numbers represent. This is the graph, but let's talk about what it means. So for let's say we have a number, it is 3 plus 4i. So what does the this number mean and what are the properties that we are or we talk about? So when we say that a number is 3 plus 4i, it means that it has 4 in its imaginary side of thing. So when we draw its graph, it would be It all the complex numbers are drawn in a plane that is the complex plane in which. So if we remember it can be easily simplified as if we remember that this is the real number line in which we used to have 0 and 1, 2, or even if we let's say have a ruler. So when we have a ruler, right, there are markings, so that is the real number line. So it is easy to explain that complex numbers are on a 90-degree to real numbers. But why is that? So, but if that can be seen by this visual. So when we multiply the number by iota, let's take any complex number. We don't know where it is present, but if we multiply it by iota, right, it would become no, 3, 4, right? And if we multiply this by iota, it will become 3 iota plus 4 iota square. Now this can be seen as iota square is equal to minus 1. We can say that this number is minus 4 plus 3 iota. This is the points that we are posted here, minus 3, 4 and 4. These are the point. Now the special point about them is they are at a 90-degree angle with each other. This means that if we multiply any complex number by iota, it is basically shifting that number by 90 degree. That is why for drawing the complex plane, we use the iota as y-axis and real number line as x. So it is basically, if we visualize the real number line, the imaginary numbers are in a plane. So they are above or below the line, not on the line for easy visualization. That is how we remember the number. So now there are also a few properties that we talk about. So let's say z is equal to 3 plus iota. So what we also do is we have three qualities that we talked about. One is the modulus, one is the argument, and one is the conjugate that we talked about briefly in the last class as well. So the modulus of z, if we see in a geometric distance, it is basically the distance between that number and origin on the complex plane. So if we assume that this is the complex plane and this is the number that we are talking about, this red distance is the modulus of z. Similarly, argument is the angle that it makes. So this angle that we have here, this angle is the argument of z. And the conjugate is the mirror image on the real axis. So if we take this point to be our number, then its conjugate will be, so this is the mirror image. So this is its conjugate, the mirror image on the this line. So the cool thing or the property that we talk about is that whenever we take a conjugate or multiply by iota, it doesn't change the number. So if we draw a circle, they all are on a circle. So multiplying by iota is just rotating the number. Now, if we multiply by different angles, so see, this is multiplication by iota. So these are on the same radius circle. And this is the quality in because of which we use the polar form representation. Because sometimes drawing this circle and using the angle theta it makes is easier to visualize and use in clear. It is like when we are talking in wave mechanics or in oscillatory motion, when things are rotating, you can basically make it so that it is like multiplying them with iota in or some power of iota. That's why it is useful to know that this particular concept of using complex plane in rotating or oscillatory motion is called phasor diagrams, and it is useful in that sense. So, for example, you have a real quantity at minus 50 or 50, and you moved it so that it is now at on some arbitrary point here. Now, using the normal algebraic representation, it would be hard to figure out every property of how fast it is rotating and stuff. But using the phasor diagram, it is very easy in comparison. For example, if a object travels along this circle, it is easier to use the angle than the distance formula to figure out how fast it is going. This is the one of the part of geometric representation of complex sum. The second thing that we talk about is using this theta. We have this particular point on the circle. It is root 3 by 2 comma 1 by 2 the point. So the number is root 3 by 2 plus iota by 2. As we multiply the iota with the y coordinate. So how do we, so what is the property? So if we see from this circle, right, this is the definition of the polar form. Let's say this is a circle of radius r. We don't know the value. And this angle that it makes is theta. We can figure out that this point, what whichever it is, based on the radius and angle, it is r sine r cos theta comma r sine theta. So this is how we derive the polar form. It is r into cos theta plus iota sine theta. This is how the polar form is defined. This is what the basic representation of geometric numbers or visualizations are. So now if we talk about adding numbers or subtracting them, it is basically adding two numbers on a coordinate plane. We can simplify that the every problem that we have. So circle is basically used to represent the form. So if let's say you have the number 5 comma 6, this is a random number that is present here, right? Now 5 comma 6 here means that it is 5 plus 6 iota, right? Now let's say I tell you that we rotated the number by 30 degrees or 60 degrees. This is the unit circle, yes, and it is the why, but it can be any circle. So the question was about this, right? R cos theta plus iota sine theta. So this is for any number. So it's not the circle, we use the circle. It is more that we know that it is possible to find it using the circle. It is basically the polar form that we have even for the any real number in 2D plane. So if we have any xy number, right? Let's say this 5 comma 6. We also have a polar form of this, right? Or let's say 3 comma 4. We have this number present here. So the polar form of this number is distance from origin and the angle it makes with it. Basically, this is the distance from origin will be 5 from the distance, like distance formula. It's basically 4 minus 0 square plus 3 minus 0 square whole square rooted. So that's how modulus is defined as well. So every property that we talked about, right? The modulus of z is square root of imaginary plus real part, right? It is basically its distance from origin. So if we take this point for example, it is root 3 by 2 plus 1 by 2. Its distance from origin will be 3 by 4 plus 1 by 4. So it's on the unit circle. So it's 1. That sort of thing. So we use the circle to know the number, and then calculations is depending on if it is useful in this form or the Euler form. We move it in different forms. So now the next point will be about talking about some an interesting problem that we can visualize. It will have to be built upon, but it's basically compound interest rates and complex interest. So let's say for first question, first part of the question, we will assume that a bank is offering you complex interest rate yearly. So it a bank says that there is, if you deposit 100 rupees, we will give, or $100, we will give you iota iota interest rate per year. Should you invest in that bank or not? That sort of question. So if we know about, if you guys like, first we can talk about the compounding interest in general. So this is how generally compounding interest grows. So for the first year, your amount will be set at one, then it will get up to 1. If this is for 12% interest rate, so let's say just make it point 1. So 10% interest rate, if it is there, then it jumps to 1.1 and it stays there for the next year. So that's how compounding interest generally works. So for the next year, you will get the interest on your 100 rupees that you submitted, and the amount of money that you get as interest, the 10 rupees that. This is how general compounding interest works, right? So now the bank is offering you interest rate of iota. Should you accept it or not? That's the question. So any intuition, like from just intuition, you don't have to calculate anything. Just from intuition, should you invest in the complex interest rate or iota interest rate?
As somebody who
This
actually has investments and I am an aggressive investor, I would definitely. And
yeah
then I will try to figure out if I actually will earn.
yeah
But okay, don't do that, kids. Like try to figure out first. But
yeah
honestly, if the okay, if we're going to talk directly about investments, invest
uh-huh.
only if you know the market is sure. However, if we're just going to talk about the complex numbers and computing, I think I would. It's a definite yes for me. If
Okay.
what you showed right now is how it's gonna go,
This is
absolutely.
this is the graph for general compounding interest. It's not for iota. For iota, it's going to be interesting graph. So
It's an up
here is,
down.
let's say you invest
Mm,
$1 for simplification. So
okay.
after first 1 year, your amount of interest will reach 1 and 1. So basically,
Mm-hmm,
you get one in iota amount or a currency that you cannot actually use.
mm-hmm.
After the second year,
Bitcoin.
now because you got the investment on even on the iota amount that you haven't reached, like that
Mm-hmm,
isn't real, you will now have all your money invested in that currency, basically. So now you have two iota amount of money and no real money if you have.
this feels like Bitcoin.
Yeah, basically that's where it was going. So if we
Uh-huh.
continue the exercise, like it's basically what in mathematical sense, yeah, it is
Mm-hmm.
basically a currency that taking your money and putting it into something that isn't actually of value, or at least not on a different kind of value than what you have. After
Okay.
the third year, you now owe the bank $2 for your $1, but you
Mm-hmm.
still have that two imaginary dollars that are
Mm-hmm.
there. After the fourth year, now you owe the bank $4 for every dollar that you had, and you don't have any imaginary dollars as well.
Mm-hmm.
But so now you go to the bank and okay, what? I you said that it will make money, and now you are, but the bank says that you should hold on. So
Yes.
now after the fifth year, you are still in loss.
Yes.
After the
Even.
sixth year, you are now lost in everything, like even
Yes.
real money, and but now your real money loss has recovered. So now you don't owe bank any real money. You just owe it the 8 imaginary rupees that it has.
Mm-hmm.
Now it is, now the bank has given you some real output, but you still owe it that 8 of its imaginary money. And after
Mm-hmm.
8 years, you get 16x returns on the investment that you made. So each dollar will become $16 after 8 years. You just have to wait in this. So now let's say the
Mm-hmm.
bank says instead of compounding every year,
Mm-hmm.
we will compound it every continuously. So every millisecond or the smallest amount of time that you can take. Now they are compounding it constantly with the same,
Okay.
because the bank saw that, you saw that after 8 years it gave 16x return. So now everyone is going to invest in this.
Mm-hmm.
So now bank said that now instead of we compounding it every year, we are compounding it continuously. Should we invest in it now? That is the second part of the question.
I'm a gambler.
Yeah.
I am a notorious gambler when it comes to this. So, and- but only in small amounts. So if I'm just going to go for, say, it's going to eternally or continuously compound my $1.
Continuously compound will be like basically
Mm-hmm.
it isn't like the 1 year it compounded, after 1 year it stayed this, right, this
Mm-hmm.
between. Instead of that, it just compounds it continuously. So
Mm-hmm.
after 1 second, it becomes your money is still increased. That sort of thing.
Mm.
Any like from what we saw in this case, what do you think? Will compounding continuously be better or be worse? We can take it as further as well. If we talk about it in real money, like real bank, instead of
Mm-hmm.
compounding it in every year, or some banks do it monthly. We just make it that every bank continuously compounds the money.
Okay, maybe no, I'm not sure if I'm understanding correctly, but basically we kind of alternate between the bank owing us money and us owing the bank money. And then also in between we have these like this weird not like non-existent currency. So
Yeah,
even if we what's the verb? Confund? Every month?
Compound. Uh-huh.
Confound, sorry. If we confound
compound.
every
Mm-mm.
month, we basically just alternate between having a loss and having a win. So I don't
No, but
see.
see this. So the difference is this particular graph, right?
Yeah.
It is increasing, even though we owe. It is a spiraling outwards, right? So if we
Mm-hmm.
do it indefinitely, the amount will
Mm-hmm.
get bigger and bigger. And if we pay out at every eighth, right, you will.
Oh, I see
It
what
is,
you mean. Okay.
yeah. So this is a good investment, right? From
Yeah.
a sense
Yeah.
that it is increasing the amount of money in the bank.
Yeah. Okay. I guess I
Yes.
just don't understand how banks work. But that
And
makes sense.
Oh,
Okay.
yes. It
it
took me a
just
few
basically
years to
spirals
figure it out.
out. So if we now
Mm-hmm.
see the next one will be 1616. So
Yeah.
basically
Yes. It will.
this whole diagram will be scaled up to 16 now.
Okay.
So
I now I understand what the actual question was. Okay. No, I'm sorry.
yeah, nah, no, it's fine.
But you were correct, Lena, in saying you have to be smart when to withdraw your money because
Yeah,
that is the point. If you withdraw
yeah,
too early, you will owe. You
yeah.
either you it's a break even that you owe nothing, the bank owes you nothing, or you might owe something. So these types of investments are only suggested to people that actually know stock markets and investment markets because
This isn't
technically,
actually something
yeah,
that
I
is
know.
happening. This is just a thought experiment for
Yes,
everyone. Yeah.
that is that thought experiment is actually a practice among. I know I had a classmate from primary school. She studied, or he, I think, No, yeah, the pronouns is he now. He is a stockbroker now, and he studied math. Um, so he had background here, statistics, calculus, complex numbers, I believe, and
Yeah.
that's how he computes the stocks, especially
Yeah.
for non-volatile stocks. This is what he uses. I remember him talking about he was trying to get people to invest, but people were like, mm, "It no," because all they saw was this downward uh the downward
Yeah.
graph. And then I read through his other research that if you invest in 15 years, I believe, it will go up. I kind of feel bad because the 15 years would have been next year. I just did not have money at the time.
Mhm.
I would have had so much more money. But anyway, but yeah, I
Yeah.
get it. I think I would say yes to your question earlier if it's going to
So
give
this
me
this
roll up.
investment is a yes, yeah.
Mhm. Yes,
But
but
if it is
it will
doing
be long, long.
continuously instead of every year or every month,
Hmm.
if it is doing it continuously,
Hmm.
then is it a good investment?
It will have to be timed perfectly for it to
Yeah,
actually be.
bank has,
Hmm.
yeah, like
Hmm.
in this universe, it is possible to time it perfectly so that
Hmm.
from the moment you invest, it will become like compounded
Hmm.
continuously. After
Yeah,
that, is it a good interest? And
I think
so
so.
we have one for a good investment, but
So
what will
add
happen?
two,
Okay, yeah, it's a
add
good
two.
What
investment.
happen? Yeah, what happens actually is it confines itself to a unit circle
Yes,
because
that's.
yeah. So what the so we can do it here. So for
Hmm.
any amount, right? Let's
Hmm.
say if we want to calculate the compounded amount, it is the principal
Mm-mm.
1 plus rate divided by 100 upon 10. Now this 100, it is based on that like percentage. But
Hmm.
if it's n as well, basically how many times you apply this rate, that's also what matters, right?
Hmm.
Basically, if we do it monthly, it will apply 12 times in a month. So this and this number are basically what the rate is. So now if we consider everything ideal, it is basically 1 plus iota
Hmm.
by n. This. So or we can even for any rate, right? We can just simply say this is r upon n. Now this is when n is now approaching infinity because we have if we take a finite amount of time we will have
Hmm.
infinite number of basically if we are doing it continuously in maths. This is what happens when you are doing a particular concept. If
Hmm.
we say that it is doing continuously or it is a smooth graph, for example, this there are infinite points in any line segment because we can go deeper and deeper or go finer and finer. So basically, if we take a set amount of time and we compounded it continuously, so the number of steps we take, they are infinite. So now as this is limiting, we can base this limit is basically e raised to the number. So it's e raised to r. This is what this limit is. So if it is 1, the number approaches e. So we can see this graph looks exponential, right? And now let's say we plot the graph.
So Shahid, Rosie has a question. So as n gets closer to infinity, It continues compounding, or does it continue compounding?
Yeah, that's so. So what n gets infinity means basically this is the number of step times you compound, right? N is basically the number of times you compound, and this is division here because how many times you apply the rate. So if we take finer and finer steps, right, that's what happens. So if you take this for example, this is the floor function, right? The floor of x. So these are the steps that we take. Now if we increase this up, the gap keeps on increasing, right? The function that we are going for, this is basically e raised to x, right? Like, see, we can see that this and this function are basically overlapping. So this graph, when n is very large, so here n is like very large amount, it's basically e raised to x, right? So back to our question. So if it is given to you that it is continuously compounding, then it is e raised to iota, the amount of, like, if you invest $1, it will become e raised to iota. Like that's the investing rate that you will multiply. Now, if from the Euler formula, we know that e raised to iota theta is equal to cos theta plus iota sin theta. And that's why that is the basic gist of what is happening. After a point, the compounding will become just a unit circle. So if it is compounded continuously, it is not a good investment because your money will never spiral out like this. It just becomes into a circle.
It'll be confined. And
Yep. It's
okay.
just like it becomes what Lena said actually. It just oscillates
Hmm.
between you owing bank money and bank owing you money. There is
Yes.
no solution. So that is like the cool part about this question, that whatever we see here, right? For example, this is where the difference sides. Yeah, it's basically if we take finite amount of steps in complex numbers, things can increase. But in ideal cases where everything is continuous, it just moves around on a circle and circle. So from an investment perspective, no, it is not a good investment, as you are just, it is basically just like saying, my money is, uh, I have that money in the safe. So overall, it will lose its value,
Hmm.
right?
Alrighty.
Yeah.
Thank you for explaining that, Shahid.
This was the investment thing. So that is sort of how the investment works. So, and also the reason why where the Euler's formula is one of the reasons where we have, this is one of the reasons or things that we have. This is why it is like important with exponential, that sort of thing.
Oh yes,
So
Rosie's
yeah,
asking
so
if
the
it
graph
relates.
is sort of like that, but it doesn't have any relation with golden ratio as such. But uh, in the next lecture, I believe we are talking about square roots, cube roots of unity. So basically, the golden ratio is this one, right? Right, and the square root of unity is basically plus or minus, there, where so it doesn't have anything to do with it, but it sort of resembles the number. So the cube root of unity is, or this is something that we will do with the unit circle as well. So let's say you want to find nth roots of unity. So first of all, we know that, if we say x square equals to 1, how many answers are there about this? So it is like this pair of two lines, x equals to 1 and minus 1. Now if we talk about x cube equals to x raised to 4 equals to 1. These two are there, and also iota and minus iota will be in the answer. Correct? For even it will be 1 this. So where we will solve the equation for x raised to n equals to 1. So for in this real plane, we will see that if I now have n equals to 1, we stop this to right. And now as we move, it will oscillate between 1 and 2 solutions. That is because it's basically if it is odd, it is 1. If it is even, it is 2. But now, if we talk about in complex plane, the rest of the roots are complex. So how with the unit circle and help of this we find the solution. So we basically divide the circle in n equal parts, and the points that we have are the roots of unity. For example, for x raised to 4, the points would be x square. There's 4 equal parts of the circle. So it's basically we know that one real one or 1 comma 0 is always going to be a solution, right? 1 comma 0 is always a solution to x raised to n equals to 1. So we move from equal angles from here. So if we want 4 equal solutions, the solutions will be 1 comma 0, 0 comma iota, minus 1 comma 0, and 0 comma minus iota. So the four roots will be 1 iota, minus 1, and minus iota. These are the four roots of x raised to 4. Like these are the solutions of x raised to 4. This is a so now we can also do it for odd numbers. So in that we get 1 comma minus 1 plus or minus square root of 3 iota by so plus is 1, minus is 1, and 1 is one solution. This is like sort of what we are going to do about in the next lecture. Solve it for n integers, basically more with the unit circle. We'll solve for n different solutions, and then there are a few properties about specifically with this particular being on a circle. So you can sort of see that okay, the sum of numbers will have a property. That is about it for what I had in mind for today. By the way, this Desmos is like it's basically a website, so anyone can use it for like if you want to visualize a particular thing. The visualization problem with this one is basically about like how exponentiating complex numbers work. So if we do it in step by step, it's basically if it is 1 comma 0, we can sort of see what is happening. So you have $1, and first time you multiply it with 1 plus iota. Now you second time you multiply 1 plus iota with 1 plus iota. That sort of thing. So this will become 1 minus 1 0 2 iota. Now we multiply 2 iota with 1 plus iota for the third answer. And that are the basically what the points are. If you see, this is the 1 comma 0. Now this point is the 1 comma 1. So it's basically 1 plus iota.